So in this video, we will discuss about the refraction at a spherical surface in which an object is placed inside a spherical surface. Suppose we have a convex surface like this, and this is the denser medium, that is the region inside the spherical surface. This is denser. Let me take that refractive index as mu2, and this one is the rarer medium. Let me take that as the refractive index as mu1. Now the object is placed in here O, and the ray goes to the curved surface, and at this point P, the refraction occurs. Before that, I have to draw the normal. Let me take C as the center of curvature of this spherical surface, and we know the normal always goes through the center of curvature. Clear? For a spherical surface, normal is through the center of curvature. And at this point P, the light ray bends away from the normal, that is, the light is traveling from denser to rarer medium. So it will take a path like this, and an image is formed in here, I. So this is the refracted ray. Pi is the refracted ray. So this is the angle of incidence. Let me take that as I, and that is the angle between the incident ray and the normal, and this angle is the angle of refraction R. Okay, let me take this angle as alpha, this angle as some beta, and this angle as some, let's say, phi. Now let me drop a perpendicular from P to the line through OI. Usually we call this as the principal axis, and let me take that point as E. Okay, let this point be F. We have E and F are almost the same, that is, we can take EF approximately equal to 0, that is, E and F almost coincide. So to make it a triangle, you have to drop a perpendicular. Okay. Now applying Snell's law at P, we have sine of angle of incidence by sine of angle of refraction is always a constant. Okay, that is Snell's law. That constant is the refractive index. Now the light ray is traveling from the denser to rarer medium, that is from the medium 2 to medium 1. So you have to write refractive index of first medium with respect to second medium, since the light is moving towards the first medium. Okay. This is equal to mu1 by mu2, where mu1 is the absolute refractive index of the rarer medium, and mu2 is the absolute refractive index of the denser medium. We have mu AB for any two media is equal to mu A by mu B, where mu A is the absolute refractive index of the medium A, and respectively mu B is the absolute refractive index of the medium B. Now these angles are very small. I, R, alpha, beta, phi, etc. are very small. So for small angles, we know, sine I, that is sine of angle of incidence, sine I, is approximately equal to I itself. That is also equal to tan I. That is, for small angles, this relation is possible. That is, for small angles, sine theta approximately equal to theta itself, and that is approximately equal to tan theta also. Sine theta is approximately equal to tan theta, and sine I is sine for for the angle of refraction, sin r equal to r itself, that is also equal to tan r for small angles. Okay, so I can rewrite this expression. Instead of sin I can write I by r is equal to mu1 by mu2, and this can be written as, when cross multiplying, you get mu2i is equal to mu1 into r. Let me call this as equation number 1. Now let me take this triangle, that is, let me take this triangle OCP. So this is OCP, and we know this angle is alpha, this angle is angle of incidence, and this angle is beta. So from this triangle, we have beta as the exterior angle. So exterior angle will be equal to sum of the other two interior angles, alpha plus I. And that will give I is equal to beta minus alpha. Call this as equation number 2. Similarly, when I consider the triangle CPI, here R is the exterior angle and beta and phi is the interior angles, and we know R is equal to exterior angle equal to sum of the other two interior angles, so beta plus phi. Let me put this as equation number 3. Now substitute 2 and 3 in equation 1. You will get mu2 into I is actually beta minus alpha is equal to mu1 into, we have R equal to beta plus phi. Call this as equation number 4. Now consider triangle. Consider triangle OEP. We have tan alpha. Tan alpha, we know that tan alpha approximately equal to alpha for small angles, equal to tan alpha equal to opposite, that is PE by adjacent. PE opposite side by adjacent side is OE, right? PE by OE. And when you consider triangle CEP, we have tan beta approximately equal to beta, and that is equal to PE by CE. PE divided by CE. And when you take this triangle PEI, triangle PEI, see this OE and OF are the same. Okay, since EF is approximately equal to 0. Actually, the measurement should be taken from the point F. Since this E and F are very close, I can take the measure from E itself. Okay, now when you take the triangle PEI, I have tan gamma or tan phi equal to approximately equal to phi, that is equal to PE divided by EI. Okay, let me put all these values in this equation number 4. So the equation 4 will become, that is, this equation will become mu2 into beta is PE divided by CE minus alpha is PE divided by OE equal to mu1 into beta is PE divided by CE plus phi is actually PE divided by EI. Okay, now here P is common in every term, so I can take that out. So mu 2 into PE in the brackets, it will be 1 by CE minus 1 by OE is equal to mu 1 into PE times 1 by CE plus 1 by EI. Okay, now cancel this PE. So the final expression will be mu 2 into 1 by CE minus 1 by OE is equal to mu 1 into 1 by CE plus 1 by EI. Okay, so let me call this as equation number 5. Now let me mark the different measurements in the diagram. Okay, that is, we have the object distance, that is the distance of the object from the from F or from E. We take that as U. See, this is U. Okay, my mu and U look the same, so I write it as U. And this is the image distance, so that will be V, the distance of the image from F. Okay, this is R, the radius of curvature. And one more point, everything on the left of E or F, I have to take that as negative. So this equation will become mu 2 into 1 by C is R, but since it is on the left of F, I have to put minus. Minus 1 by OE is again U, since it is on the left of F, I have to write minus U, is equal to mu 1 into 1 by CE is minus R plus 1 by EI, you have to write it as V because it is on the right side of F. Okay, now multiplying, you will get minus mu 2 by R. This minus and minus will become plus, and if I take mu 2 to inside, it will be mu 2 divided by U equal to minus mu 1 by R plus mu 1 by V. Now take this term to the left and this one to the right. I'll get mu 1 by R minus mu 2 divided by R is equal to mu 1 by V minus mu 2 divided by U. So the final expression is like this. Let me write the right hand side first, that is mu 1 by V minus mu 2 by U is equal to, here R is common, denominator is same, so that I can write mu 1 minus mu 2 divided by R. Okay, so this is the expression for the refraction at spherical surface when the object is placed in the denser medium, that is mu 1 by V minus mu 2 by U equal to, this is mu 1. Okay, mu 1 minus mu 2 by R. Clear?